have you ever just stopped and wondered how a modern game engine juggles dozens of super complex systems? We're talking everything from graphics to AI, without just completely collapsing into chaos? Well, today we're going to pull back the curtain on V-Engine's really elegant solution to one of the biggest challenges in game development: how to tame that very complexity. At its heart, an engine is really just a symphony of specialized systems, right? You've got one for rendering, one for physics, audio, input, you name it. And they all have to cooperate perfectly 60 times a second. So the big question is, how do you architect all of this without creating a tangled, unmanageable mess? V-Engine's answer is actually surprisingly simple. It's a strict, top-down approach to control and communication. So, the very first principle is a super clear separation of powers. You can think of it like a well-run company, you know? You don't have the CEO personally managing every single little task. No way. Instead, you have a clear hierarchy where the high-level strategy is totally separate from the day-to-day operations. In V-Engine, this means the main engine class is kind of like the conductor of the orchestra. It handles the big picture stuff, the application lifecycle, the main game loop. But all the heavy lifting, all the nitty-gritty of managing every single individual system, that gets delegated to a dedicated coordinator, the system manager. And listen, this isn't just some afterthought. It's a foundational design principle. As this quote right from the design doc shows, the whole goal is to keep the engine's role clean and focused. You let the system manager handle the complex dance of all the systems themselves. And the scale of this operation is, well, it's massive. We're talking over 30 core systems registered into what's basically the engine's entire vocabulary. You can see some of them here, from foundational pieces like the config system and timing system to heavy hitters like render and physics, and even gameplay systems like AI and audio. And the system manager, it's the master of them all. Okay, so how in the world does the system manager wrangle all these different systems without creating a tangled mess? It's simple, really. It makes every single one of them sign the exact same non-negotiable contract. This unified contract is the key to everything. And that contract is called the iSystem interface. The best way to think about it is like a universal adapter. It lets the system manager plug into any system, no matter what its specific function is, and control it in a perfectly standardized way. Every system speaks the same basic language of control. This contract boils down to 3 core commands that every system has to obey, which are provided by a common base system class. First, there's init, which is called just once for resource acquisition. Second, you have update DT, called every single frame to do its logic. And finally, shutdown, called once at the end to cleanly release everything. It's predictable, it's simple, and it's universal.
Now, here is a critical, absolutely non-negotiable rule. All of this high-level management happens on a single main thread. Why? It's to prevent what we call race conditions. Just think of it like 2 people trying to edit the same Word document at the same time. You'd get corrupted data, right? So by keeping these core lifecycle operations sequential, V-Engine guarantees the game's state stays perfectly consistent.
And that sequence is anything but random. Initialization follows a very rigid system priority scale, where the lower numbers always boot up first. So, systems with a low priority number, like config and timing, down at priority 0, are absolutely guaranteed to be ready before higher-level systems like the render system at priority 25 even think about starting. Okay, so we've got dozens of systems. They're all following the same rules, and they're booting up in the right order. But how do they actually do anything? The answer is that data is the glue that binds all of their logic together. V-Engine uses this really clever pattern called Inversion of Control. Think of it like a library. The systems are the readers. They contain the logic for how to process information. But they don't own the books. The data, the books themselves, are all stored in a central library. Each frame, a system just checks out the data it needs, operates on it, and then returns it. So here's how that actually works under the hood. The system manager creates one single central data repository, an EnTT registry, which holds all the game state components. Then, it manually injects a pointer to this registry into every single system. This clean separation is an absolute game changer. It means you can test the system's logic in total isolation, and it makes the engine way more scalable.
So how does all this come together in a single frame? Well, the result is this beautifully predictable and auditable update loop. It's a deterministic pipeline where every single action happens in a precise, repeatable order. And this isn't some abstract concept, it's the literal sequence of updates happening in the code. Every single frame, without fail, the engine pulls platform events first. Then it reads input, then it updates AI behavior, runs the physics simulation, and only then does it render the final result. This fixed order makes debugging 1,000 times easier.
Of course, systems do need to talk to each other. V-Engine gives them 3 distinct channels for this. For systems that are really tightly linked, like health and combat, a direct reference using getSystem gives you instant, tight coupling. For broader notifications, like a character's death triggering a sound and a UI update, the event system just broadcasts a message without coupling the systems directly. And for the heavy stuff, like complex physics, the job system offloads the work to other threads.
So, what are the actual payoffs for all this architectural discipline? Let's look at 3 key areas where this structure really shines: error handling, frame timing, and platform abstraction.
First up, error handling. Instead of getting some cryptic, generic error message, you get a clear, classified report from a centralized error system. Did the physics engine have a meltdown? That's a physics error. Did the renderer fail to create a texture? That's a graphics error. This structured approach turns debugging from a wild guessing game into a precise science.
Next, frame timing. The timing system provides this high-resolution, nanosecond precision delta time. This value, like 16.67 milliseconds for a 60 FPS target, isn't hard-coded. Nope, it's pulled directly from the config system. This means the entire engine simulation speed can be adjusted from a single config file, ensuring your physics and animations are always consistent. And here's a perfect example of how these dependencies work in practice. The platform system, which cleanly separates all the SDL3 window management from everything else. It depends on the config system to know the window size. Then, in turn, it provides the window handle as a service to the render system, which obviously needs it to draw anything. It's a clear, hierarchical flow of information. Ultimately, all of these architectural rules really serve one purpose. Just like the documentation says, mastering this approach lets you build a foundation that is so modular and scalable, it can handle immense complexity, like simulating tens of thousands of entities without even breaking a sweat.
And that is the final takeaway. By enforcing a strict separation of concerns, a unified contract, deterministic ordering, and centralizing data, V-Engine transforms what could be pure, unadulterated chaos into a system that is predictable, highly testable, and just built to scale.
So, this architecture provides the solid bedrock for managing the systems themselves. But it raises a brand new, fascinating question. If all these systems are forbidden from creating messy dependencies on each other, how does anything actually happen? How does a physics collision trigger a sound effect on the complete other side of the engine? Well, that's the puzzle we're going to solve in our next explainer.